Okay, so this is the third and last lecture on convex ancient solutions of curve shortening flow. I've written here to remind you the equation for a curve parameterized by gamma. The speed is equal to minus kappa times nu, kappa the curvature, nu the upward pointing unit norm. And the idea was to show, to classify all convex embedded solutions. The previous time we did the compact case. Today we're gonna do the non-compact case. So we're gonna see the theorem along with Langford and Tinaya that says that the only convex embedded ancient solutions to curve shortening flow are, well, the two compact ones we had from the previous time. So the shrinking circle. Okay, remember these are the circles with radii squared of minus 2t. T goes from minus infinity to 0. The angular oval. These were characterized by curves gamma t. The evolving curves are x, y, such that cosine x is equal to e to the t hyperbolic cosine y. Okay, and here again we have t from minus infinity to 0. And now we're going to add two more. That is the stationary line. And the Grim Reaper. Grim Reaper, which we're going to use here. So I'm going to denote as GT, the time slice. And this is equal to points x, y, such that cosine x is e to t minus 1. Okay, this was a graph of log of cos of x. Okay, translated in time. Okay, and remember this is always modulo space-time translations, spatial rotations, and parabolic rescale. Okay, so let's look at the proof of this theorem. And as I said, even the compact case, this is we can use like a different proof. The major ingredient is Shu-Wang's dichotomy. That says that for ancient solutions, as long as the curvature is bounded, they lie in strips. Here, okay, we would just like in one dimension, or they sweep out R2. Now, it can be shown that in this case, we only get the shrinking circle. So we're gonna focus on the other case. Okay, so what is, again, like as we've done so far in these lectures, we're not gonna give precise proof, we're just gonna give the sketch of the proof. So, and because since we've done like the compact case, let's just focus on the non-compact case here. So I'm gonna look at the non-compact case. All right, and let's take gamma t, an ancient solution. And we're gonna assume that this lies in the slab pi, that is x and y in R2, such that x, the norm of x is less than pi over 2. Okay, our standard slab. All right, so here's my slab, and the solution is non-compact and lies in here. Okay, so I draw it like the Grim Reaper, but we don't know exactly how it looks like. Okay, note first that the Gauss image of gamma t is equal to minus pi over 2, pi over 2. Okay, this should be true for every t. Since I have a compact curve, we see that as we go up here, the normal should be getting horizontal. Okay, as we go to infinity. Okay, so I can use this parameterization gamma from minus pi over 2 to pi over 2 by turning angle times minus infinity to 0 to R2. This is the parameterization, a parameterization. And we're gonna let PT to be equal to gamma 0 t. Okay, this point PT is a point whose normal the outward pointing unit normal is equal to minus E2. Okay, I'm gonna name this point PT. And by a vertical translation, we can assume that this point passes through the x-axis at time t equals 0. Okay, how am I going to write this? I can say that by a vertical translation, y pi 0 equals 0. Okay, so we want to show that the only such solution is the Grim Reaper, right? Of course, we are looking at the case that we have something that is strictly convex. I didn't mention this. So kappa is always positive, and therefore the line is not the vertical line is not an option here. Okay, so we just look at kappa positive. All right, so the first thing we're gonna show is that around here, so we're gonna show first that around here, around PT, our solution looks more and more like the Grim Reaper as t goes to minus infinity. And then we're gonna use this to show that in fact, everywhere it looks like the Grim Reaper, and it is a Grim Reaper. Okay, so this is the first step. We will show that gamma t s, this is gamma t plus s minus ps, the limit as s goes to minus infinity. Okay, so how do you think about this? You take your time slice gamma t plus s and you translate it by ps. So think of the case t equals 0, then you take gamma s, or here like in the picture, you take gamma t and you take this point, you put it up here. Okay, so this will be the gamma 0 upper s, but you do this with the whole flow. So as you let s go to minus infinity, it's not difficult to show that this converges to a Grim Reaper. Okay, and how do we show this? Well, we can show that, gamma theta t plus s minus ps has curvature well, what is the curvature of this point? The translation doesn't matter. So the curvature is equal to kappa theta t plus s. Okay, so as s goes to minus infinity, this here converges to something that is independent of t. Okay, it always converges to kappa theta comma r, let's say when r goes to minus infinity. Okay, so therefore this implies that the curvature of the limit is independent of time. Okay, so the curvature of the limit is the curvature of this guy as s goes to minus infinity, and it is independent of t. But when you have a solution and the curvature is independent of time, this implies that it is a translating solution. And we know that the only translating solution is, well, convex is the Grim Reaper or a scaled Grim Reaper. Okay, therefore I left like the space here because I want to add here converges to a scaled Grim Reaper. Okay, so here this implies scaled Grim Reaper. So the Grim Reaper we said is GT. Well, when I scale it, I have to scale parabolically. So I get R times R to the minus 2t. Okay, let me fix that. Okay. R minus 2t. Okay, and t is in minus infinity plus infinity. Now this scale Grim Reaper lies in a slab of width r, and therefore r has to be 0, 1. Okay, but also note, what is this r? Well, this is 1 over the curvature at the tip. In particular, so 1 over r is equal to the curvature at 0. Let me write kappa infinity to indicate that this is the curvature of the limit. At 0 means that at the point where the normal is minus a2, and this is equal to the limit as r, or let's not put r, let's put tau. As tau goes to minus infinity of kappa 0 tau. Okay, so I can add here that r is in fact the limit as tau goes to minus infinity of 1 over kappa 0 tau. Okay, so we know that around the tip we do get a Grim Reaper, but we just know it's a scaled one so far. So the next step here, too, is to show that in fact this r is equal to 1. Okay, so our next step is to show that r equals 1, so that indeed at the tip we do see the honest Grim Reaper. Okay, and this is gonna be done as follows. So let me draw here our solution. This is our x-axis. And let's assume we get, well, we don't know what r is, but I'm going to draw it as if it is less than 1. Okay, so the edge of the solution looks like this. Here we see a scale Grim Reaper, but up here we know it goes very close to the two parallel lines, right? Okay, so now what are the distances here? This is 1 over r, sorry, r, right? This is the width of the Grim Reaper. Let me just put another color. Okay, this is r here. And this distance is 1 over r times minus t. Okay, very sorry, this is not a good color. Let's just change it. 1 over r times minus t, and this is r. Okay, so let's look at the area here. Okay, this yellow area. Okay, that's not a very good color. And call this a t. Now, by the evolution by curvature, we know that minus a prime t is equal to the integral of the curvature on gamma, let's put prime, let's put tilde. Where gamma tilde, I mean everything that is below the x-axis. Okay, so gamma tilde here is equal to gamma intersection y less than 0. Okay, so I'm integrating this orange bit, and because the normals here, they're almost by the convergence to two parallel lines as t goes to minus infinity, for small enough t, this integral of kappa, which is the difference of the two normals, it is as close as we want to pi. Okay, so what do I mean here when I say as close as I want? I mean that for any epsilon, there exists t epsilon such that minus alpha prime t is less than pi plus epsilon. Okay, and this should be true for any t less than t epsilon. Okay, this now integrating implies that a t is bounded by p plus epsilon minus t plus some constant. I don't care. Okay, but this area, we can make it as close as we want to pi times minus t. Right, now on the other hand, if I look at the green guys here, okay, this r and 1 over r, and try to compute the yellow area by using this, what do I get? I have, okay, let's try red now. I have this trapezoid here whose area is like r. Sorry, this, when I say r, I mean this should be r times pi, right? So we scaled the Grim Reaper by r, so the width becomes r times pi. Okay, so this area is like r plus 1 times pi over 2 times 1 over RT. Okay, but if we see what this is like 1/2 plus 1/2r pi times minus t, which, and this is bigger than 1 unless r is equal to 1. Okay, so this is strictly bigger than 1 unless r equals 1. Okay, so we see that if we assume that r is less than 1, then for t small enough, we get a contradiction by counting the area in these two different ways. Okay. Right, because as we said here, you can take the epsilon to be as small as you want. Okay, so this gives us that r equals 1. And the next step is to show reflection symmetry. Okay, so how do we show reflection symmetry? This comes from the fact that the tip of our solution becomes reflection symmetric. Okay, and here's the argument. I'm going to draw the solution again. Okay, let's put the x-axis. And I'm going to add now this line, purple. Let me put the y-axis as well. Okay, so this is our y-axis, and next to it, I'm going to draw this line. Which is x equals alpha, okay, for some alpha. Okay, and right, so what we can observe is that our solution gamma t intersection h alpha would be this half plane. If I look at this bit on one hand, and then reflect the rest of it along the x equals alpha, then the black and the green, they are disjoint. Okay, this is true for t small enough. Okay, so this is our alpha mean reflection along the x equals alpha line. Okay, so the two are disjoint for t less than t alpha, for some t alpha small enough. Now, why is this the case? This is the case because around the tip here, my solution is reflection symmetric. Okay, it becomes the grim Reaper, the honest Grim Reaper. Okay, so we know that we get something that is as close as we want to reflection symmetric, and we also know that up here we converge to the two parallel lines. Okay, so the green bit, which should stay away from this x equals minus pi over 2 line, cannot intersect the black line of our solution. Okay, this is true for t small enough, and by the maximum principle, this means that this should stay true for all t up to 0. True for all t less than 0. Okay, now we can let alpha go to 0, And we can also do it on the other side. And this implies that we get our reflection symmetry. Okay, you see what I mean here? If you let the purple line come to, the middle, then this means that the right part of our solution, after reflected, stays above the left part. But then we can do the same thing on the other side, and we get our conclusion. Okay, and the last bit we have to prove is that our solution gamma t is in fact equal to GT. Okay, the Grim Reaper. Remember this GT denotes the Grim Reaper solution. Okay, so how do we do this? Now, the idea is as follows. So I'm gonna draw, here's my Grim Reaper. And assume that you have another solution. That's okay. The idea is to compare this part of the Grim Reaper. Sorry, not this part. Yeah, sorry. The left part of the orange solution has to be compared with this part reflected. Okay. Well, and of course, like this is, since the Grim Reaper is reflection symmetric, this doesn't make sense. But again, to make sure that we don't have problems with the boundary, what we're gonna do is we're gonna reflect along a line that is slightly off. Okay, so we're gonna look this black part, the reflected black part of the Grim Reaper, and compare it with the bold orange underneath. Okay, now for this, to be able to do this, is we have to control how these two tips move. And as long as we can say that they stay apart, then we can do the same trick as we did before with the reflection symmetry and contradict the maximum principle. So all we need to do is check how these 2 points move. And this is a result of the fact that if we look at this quantity L of t to be the distance of this point that whose normal is minus a2, then if we look at ddt of lt plus t, this is equal to L prime plus 1. And remember, L prime, this is equal to the, sorry, minus L prime is equal to the curvature at this point. But this, we know, is always bigger than 1, because 1 is the limit of this curvature as t goes to minus infinity. And we know that it's increasing. Okay. So therefore, this here, L prime of t plus 1, okay, is less or equal than 0. Okay, so this implies that LT plus t is non-increasing, and therefore the limit as t goes to minus infinity, LT plus t exists. Okay, it might be infinity, but we know it exists. Okay, therefore, we can, by doing what I was explaining in this picture, we can show that LT plus T, sorry, this limit of LT plus T is equal to the limit of L of the Grim Reaper T plus T. Okay, so this is P of the Grim Reaper. Yes, T goes to massive. Okay, because if they are not the same, then the one tip lies above the other, and we can play this trick that this picture shows. Okay, now if they are the same, then we can do the same thing by shifting time a bit. Okay, so you consider gamma tau of T to be equal to gamma T plus tau. Okay, and repeat the argument that I just explained. So if you look at now this gamma tau, then you get a contradiction for this guy, because when you look at this limit now for these guys, they cannot be the same as the Grim Reaper. Okay, and this finishes the sketch of the proof. Let's just go like one more time through the steps. So we wanted to prove that if you have a solution that lies in a strip, then it has to be the Grim Reaper, convex, non-compact. What we did is first, we showed that around the tip here, the solution looks like a Grim Reaper. We did this by looking at translations of this point at the origin, taking a limit. We get a translator. We showed that then it has to be the Grim Reaper. Well, this is the only convex translator in dimension 1. And then the next step was to show that, in fact, this is the honest Grim Reaper. So it's not a scaled one. And we did this by looking at the area that is between the x-axis and our solution and counting it both ways, 2 different ways. Once by using the equation and taking this formula here, and the other one by assuming that the tip moves with speed faster than 1. Okay, then once we know that the tip is reflection symmetric, we can do this trick with the reflection and prove that the whole solution is reflection symmetric, and then we can compare it with the Grim Reaper again by using reflection symmetry. Okay, and I will stop here. Thank you very much.